What we talked about was electric potential being the measure of the volt. That's what we call electric potential, and voltage potential energy, and what controls potential energy and electric potential in the X-ray tube. And it's the power behind the movement of the electrons. Remember, the number of electrons that we move is what we refer to as amperage. The voltage is kind of like the power behind it. So we have to have both of them. We're going to talk about how we can manipulate the two here in just a bit. We talked about, well, let's talk about, back up, I started on the wrong page of this. So that was the last thing we talked about. So the number one, we talked about the number one function of the X-ray imaging system was to convert electricity to electromagnetic radiation. And we talked about electrostatics, which are stationary electric charges. We talked about the three ways that we can electrify something, and that was through friction, which is essentially rubbing. You walk across carpet, you pick up electrons, bless you. And then we talked about contact, which is where it's really equalization or spreading of the electrons that you've scooped up to something else, and that's contact. And we talked about induction, where you've got enough electric charges that electrostatic charge, which is, essentially your voltage and number of electrons that you've got because of, them being concentrated inside your body, that'll actually jump kind of like a miniature lightning bolt. We talked about what electric ground was, that whenever you get that contact and the induction and that equalization, redistributing where it goes into the earth, that is an example of an electric ground. And we'll talk a little bit more about that in electric circuits here in a minute, and I'll relate a couple of funny and yet embarrassing stories. One was embarrassing for me, and the follow-up was stupid stuff sometimes is generational. The other one is my son. And it was hilarious for him, to me, for him. So anyway, we'll talk about electric ground is basically where electrons can go, right? So the net charge of the universe or the earth is neutral. So all discussion of electricity revolves around the electron. That's negative charges. Electron and negative charges outside, easily moved. You can't really move the proton without moving the element or the wire or what it is that you're using. So anytime we're talking about electricity, we're talking about electrons, and just equate the two. So anytime something has either too few or too many electrons, then you're electrified in some way. You're ionized and yet you're electrified. If you have too few electrons, then you're positively charged. If you have too many electrons, you're negatively charged. So it's all about the electrons. You have a dissimilarity between protons, positive charges, and electrons, negative charges. You're electrified. If they're even, then you're not. So we'll talk about the electrostatic laws, and those were that like charges repel and unlike charges attract, right? We talked about Coulomb's law, and Coulomb's law really had two parts to it. And that first part was that the electrostatic charge was equivalent to the number of electrostatic charges, right? So the more electrons you have, the greater the electrostatic charge. But we also talked about the electrons, since they're all negative charges, they push each other apart evenly, and they're going to distribute evenly on the face of the surface. So that's just the next thing. But the back to Coulomb's law, the more charges you have, the more charges you have, but the further apart they are, the less charge you have, right? So and the distance between them follows the inverse square law. So then we talked about concentration and distribution. That's what I was just talking about. Distribution is even on the face of a conductor. We'll talk about what a conductor is here in a minute. But they concentrate on the sharpest curvature, and we'll talk about that. Any questions on all of that before we press it?
What did you say, Coulomb's law?
Coulomb's law? Yeah.
There's two parts.
Yeah.
The first one was the electrostatic charge. What was the second part?
the electrostatic charge is inversely proportional to the square of the distance between them. So the further apart they are, the less charge you have. Yeah. Anything else? Okay, now we're going to talk about electrodynamics, and that's the study of moving charges. And so you look at your battery, and just any old battery, let's just say car battery, and you've got two posts on it, right? You got a positive, you got a negative, right? So whenever they were first studying electricity, they really thought that the electric charge was positive. Now we believe it to be negative. But you're looking at your battery, and which one's the hot side? Positive, right? That's where the electrons flow from. So don't let that confuse you. You know, look at your battery or anything like that. You know, that's basically your ground. If you're jumping a car off, you have to plug on. You know, if battery's dead and you put the cables on, you have to put the cable on the positive terminal, but the other one you can ground to the car. So that's ground. So it seems a little bit backwards. So if that kind of confuses you, just think of the positive post being a positive flow of negative charges, if that's helpful. So if you picked up the Carlton book, he kind of goes into that, and he kind of overstates it a little bit and points it out several times in a similar chapter. But that doesn't really matter to us. What we're going to say is that electricity is negative charge, and in the discussion of electricity and electric flow, some of the textbook authors will talk about which way things are flowing and all that. What we're going to say and what the effect of voltage is whether it's a pushing, or a pulling effect. So what we're going to say is, it really doesn't matter for the registry, but what we're going to say is electrons are negative, voltage is a pushing effect. So it's kind of like, you're looking down the freeway, the cars are the electrons, the motors, drive the electrons, right? So that's your analogy, is the pushing effect of the motor in the electron, the pushing effect is the voltage, and the whole car is the electron. So, and that's the current, the number of cars you have on the freeway. So, originally thought as positive. Now we, kind of know that they're negative, and it's really a perceptual thing, I suppose, more than anything else. So things that we have to have in order to control electricity is that we have to have a pathway for them to go. So I told you we were going to talk about electricity, kind of, we were going to talk about water kind of as an analogy for electricity, right? So you look up in the sky during a storm, you see a lightning bolt, and it just goes straight across the sky, right? No, it does not. It goes all over the place. That's because, like a river, lightning is going to follow the path of least resistance. So whatever is in the atmosphere that's making it do that is causing that path of least resistance. So I have a runoff creek running across my property, and it just winds all over the place. It comes from multiple directions, and it makes turns that just don't seem logical to me. It just seems like a stream of water should just go in one direction, but it doesn't. For whatever reason, you've got features, be it a tree, rocks, or something in the soil that redirects the water, and it follows the path of least resistance. It's a whole lot easier to wash dirt away than what it is a rock or a tree, right? So it follows path of least resistance. So if I were to have electricity and I just try to shoot it across the room, where would it go? Do you know? I don't. I have no clue as to where it would go. I just got this electrostatic charge and all these electrons. I release them. I can't control where they go. But if I give them something that has also electrons. Everything has electrons, but the electrons are relatively loosely bound to the very outside of that thing. And then I add more electrons to it, then where are then? I extend this out. You can't, cat-like reflexes. I add more electrons here. Where are those electrons going to go? Just straight down, right? So what do you call the guy that is driving a train? Conductor, right. So this is what we refer to as a conductor. Conductors allow electrons to flow, all right? So they got to go somewhere. But again, electricity follows the path of least resistance. And that path of least resistance is going to be controlled by a number of different things. So like copper is a really good conductor, but if you've got 200 feet of copper, all right, and then you've got maybe 1 foot of copper, in order for these electrons to get down 100 feet of copper, they're going to meet a lot of resistance. Okay, so the reason that we have heat anytime that we send electrons down a conductor is because those think of them kind of like tires, wheels, right? As they're moving down that conductor, it's just like tires on your car. They heat up, right? So they're going to get hot, right? So anytime we send electrons down a wire, they're going to get hot. The longer that conductor is, the more resistance we're going to have. We always have resistance. No matter what we're using as a conductor, we're going to have resistance. But anytime we're sending those electrons down that wire, we're going to meet resistance. Okay? So we've got 100 feet going that way. So we have 100 feet worth of resistance as opposed to we have 1 foot of resistance here. What's your path of least resistance? No 1 foot. They're going to have a tendency to make a turn right here. And if they've got something down here that those electrons can go into, then they're going to make that turn. Okay. So if let's say, let's dial it back in just even a little bit tighter. Let's say you're doing some home remodeling. Is it important to know where the electric lines are in your wall before you start, hammering, driving nails, screws, sawing, all that kind of stuff? Answer is absolutely. You drive a nail into your wall and you hit that wire. What's the nail made out of? Metal. What's the wire made out of? The wire allows electricity to flow, right? Would the nail? Answer is yeah. Yeah. So you drive a nail into that wire and it breaks through the insulation, and we'll talk about that here in a second. Now you've got a path for the electricity to flow through the wire, and now you've got what we refer to as a short circuit. Suddenly, whatever's down there doesn't work anymore because you shorted it out. Okay? So what we have to have then, in order to keep those electrons going that direction, is we have to have something that does not cause what we refer to, again, as a short circuit. We have to have something that's not going to change the resistance or give the electricity a different path to go on that would, be a path of lesser resistance. So we have to have conductor, that's your wire, but we also have to have something around the conductor, and that's what we refer to as insulation. So the insulation, this is a conductor, the wire. The insulation surrounds the wire, all right? So insulation surrounds the wire and it contains those electrons. The wire allows the electrons to flow, but the insulator disallows them to flow. But wait a minute, they're still going to flow inside of the conductor. Yeah, it's going to disallow them from flowing out of the conductor unless you break it, right? Unless you break the insulation, you drive the nail into it, now the electricity is going to go in a different direction. So insulators stop the flow of electricity, and how we use those is we put them around the wire so that the electricity can't escape from the wire until it gets to where we need it to be. So these are made out of plastic, sometimes made out of rubber, something like that. Rubber's going to play a very important role in what we're going to talk about here in a minute. Okay, so insulators allow the flow. I'm sorry, disallow the flow. Conductors allow the flow. All right, you got to have them both. You also have to have some sort of electric ground. This has to be grounded somewhere. So, you look at the plug in the wall, and what you've got basically are positive and negative terminals. A ground, right? And inside of there, you've got conductors so that whenever you plug your, your phone charger into it, electricity can flow out from there. All right. So, you got to have a ground, got to have a conductor, got to have insulators. So, anybody ever dealt with electricity? No, it's a joy. It's really not all that hard if you just, think about your path of least resistance. You kind of, if you're doing some sort of electric work around the house, you kind of figure it out. So, I used to live in a house. All right, a little bit about me. I've got goats. I've had goats. I've got goats on the backside of my property, and they, they're in their separate fenced area. Previously, I lived on, not now, but years ago, I lived on 3 of the rockiest acres that you've ever, wanted to live on. I tore up lawnmower after lawnmower after lawnmower, trying to mow this piece of property. And I had to use this, it's 3 acres, and I had to use push mower because I wasn't going to destroy another riding lawnmower. They're expensive, so I use push mowers and tear those up. They're only $100 as opposed to $1,000. So after a few years, I got tired of destroying lawnmowers, so I got this bright idea. I'll fence it all in. Most of it in is 3 acres. I'd fence in about 2.5 of those acres. And I put goats on it. Goats, they do a phenomenal job. People rent goats to clear out areas. All right. So I fenced all this in. I had some big dogs too, so I put up a 6-foot chain link fence, and then I went around that with what they call sheep and goat wires, 4 feet tall. Small holes. Your 2 biggest responsibilities as a goat owner is to keep them from escaping, because they're escape artists. That's number 1. And number 2, keep them from killing themselves, because they're really curious. They get into everything. And whoever said that curiosity killed the cat never met the goat, because that would be the same. So I fenced in, had the dogs in one place, had the goats in another place. I'd open the gate and let the goats into the dog's place periodically so they'd eat the grass. They're great for eating poison ivy, doesn't hurt them. But the problem with that is that my property was kind of pie shaped. All right, so it was kind of shaped like this. This was all wooded. The house was roughly here. The fenced in backyard went like that, right? And the rest was pretty heavily wooded. So it's not scale, but at any rate. So I'd let them in here, but the problem is the house had a back patio that went all the way across the length of the house. Part of it was enclosed and covered, and part of it was open. Goats are also extremely social. Okay, if you only have one goat, he's going to want to be in your lap all the time. Okay, they're a herd animal, so you got to have not just one, you have to have multiple. And even if you have multiple, they're going to try to come see you, especially if they're bottle babies. If you feed them, when they're little from a bottle, they become puppies pretty much. They follow you everywhere, get into everything. So they would get on this back porch, and where goats are, goat poop is. You don't want them on your back porch because they just eat and poop. So they eat and poop, try to kill themselves, try to get out. That's pretty much all they do, their entire existence. So I wanted to keep them off of this. This is a covered porch. They would break the screens and get inside of there too. So I wanted to run an electric fence wire all the way down the length of this. All right, so I put an electric ground here. this was my garage right here. So I put a grounding post here, and I put electric fence going all the way down, and you've got to complete the circuit. So what I had to have, this is like you're looking at the ground level outside, grounding post, and then the back porch, what I had, and grounding post went way down into the ground, but grounding post, electric fence generator out here, and what I had to have is electric fence go all the way down the length of the house and come back. So it was double, double wire. One close to the ground, one a little bit higher. And it worked great. Goats will stay off the back porch because they get zapped. Electric fences use exactly backwards of that, low amperage, very high voltage. Kind of like that stimulator I was talking about the other day. It doesn't really do you any damage, but it hurts when you get hit with it, right? So this thing has like 1500 volts, almost no amperage. So it pops you real good, but it doesn't do you any damage, okay? So I put that up, and I kind of tell on myself sometimes. Sometimes to get the goats afraid of it, what I'd have to do is pull them into it. Okay, so the goats get zapped, I get zapped at the same time, so I'm not putting them through anything I'm not going through too, right? But then they'd stay away from it, and then I could unplug it. I didn't have to run it, and it wasn't until they started getting on the porch that I'd have to do it all over again. So they're doing it all over again. I need to get my electric fence going again. So I walk outside and I plug it in. And I'm also a cheat. Somebody, you can buy these electric fence testers. And I've got one now, but you can buy these electric fence testers at like $10. Okay, but I'm an electric fence tester. All I got to do is touch it. All I got to do is touch it with the back of your hand real quick, and see if it's on, right? So I didn't have one. I didn't have an electric fence tester. So touch it, nothing. Touch it again, a little bit slower this time, nothing. Reach over and grab it, and I can feel just the slightest tingle. Like, okay, I got a short somewhere. Because what happens in a short circuit on an electric fence, most of the time what happens is grass has grown up. Okay, what's grass? It's a preferred weed, but it's wet, right? Except for now, it's pretty dry, but it's full of water. So is water a conductor, or is water an insulator? We'll talk about that in a minute. In its natural state, it's conductor. Okay, more on that in a minute. So if a weed or grass grows up and it touches that, now you've got a path of least resistance where the electricity can go straight down into the earth, and the rest of that might have some electricity. It's not going to have 1500 volts. Okay, so I'm thinking, okay, I got grass. So I walk by and I pluck up all the grass that I think might be touching an electric fence. I'll walk down and make sure that there's no wires from the covered patio touching the electric fence. It's good. All right, I'm going somewhere with this. So I touch it again. Nothing, I touch it a second time. Slower, nothing. I grab it. Slight tingle. All right, so still something going through it. Still got a short circuit, so I think. I'm not thinking is the problem. I'm outside. I'm on a patio that's covered with goat poop. What do you suppose I'm wearing? Shoes. What's on the bottom of your shoes? Cover. Right. Still not thinking. So what do? Well, there could still be something, that lower wire is only this high off the ground. Okay, so I'm looking down on it. Am I seeing everything that could be at the same level from this angle? Answer is no, not really. So what do? Use sight. Got it. Yeah. So I get down on my hands and knees, right? And I'm walking by on my hands, and I don't want to do this because, it's covered with poop. covered, but it's got some poop on it, so I'm crawling by looking, and I get up against it, and sure enough, it's working quite well. I got blasted, right? So fast forward probably, I moved out of the house. I don't know. My oldest son, he's now 31, and he was pre-high school at this point. So again, generational stupidity. So he calls me up. His dogs were getting out of the fence. He said, and I gave him my electric fence generator because I didn't need it anymore. He calls me up. He said, "Dad, the electric fence generator's not working." He said the dogs were getting out. I checked the wires, plugged it back in, and tested it. I said, "How you testing it?" "I'm touching it." Now I'm getting excited. I already told you I shot him with paintballs for a couple of years, right? So now I'm getting excited. And the funniest thing is my younger son happened to be at the house at the time. I said, "Let me put you on speaker." Any younger brothers in here? Or younger brothers or sisters? Okay. Especially if you're your younger brother, there is nothing funnier than hearing your older brother scream in pain, right? It's just hilarious. As long as he's not truly hurt, right? There's just nothing funnier than that. So I'll put him on speaker. I'm a young brother too. All right. So he says, the electric fence generator's not working. I said, "I bet it's working." He said, "No, it's not working." I said, "How you testing it?" I said, "I'm touching it." I said, "Okay. Why don't you go back outside?" I said, "Are you wearing shoes?" He said, "Yeah." I said, "Okay, I want you to go back outside." I said, the shoes are, insulating you. It's working just fine. Shoes just, and the funny thing is, no, I don't want you to. See if I got to jiggle it around. Maybe that'll make it keep going. So he says he's wearing shoes. I said, "Well, they're insulating. It's working just fine." He said, "No, that can't be it." I said, "Okay, do this." I said, "Go back outside. Touch the chain link fence." I mean, he set this up. You can't blame me for this. He set this up. I said, "Grab the chain link fence and then reach down and touch it." And the scream he let out was, I think my younger son might have almost passed out, laughing so hard. But it was hilarious. So the problem here is that the electric fence generator has no insulation. Or the electric fence has no insulation, right? So you have to keep stuff away from it so that you don't cause a short circuit. If it had insulation around it, it wouldn't shock the goats, right? It would keep all the electricity inside. So it wouldn't shock the goats, it'd be completely ineffective. So you have to have both if you're going to run wire through a house. If you want access to the electricity at any point, like an electric fence, you can't have insulation. So you've got insulators, you've got conductors, right? And then you've got what we refer to as semiconductors. Okay, heard of semiconductors? You got them in your phone, right? You got them in every computer. So usually there's two words that precede semiconductor, and that's usually silicone-based, right? Silicone-based semiconductors. And we use those. So what we're going to talk about today is not just this, but we're going to look at introduction to voltage rectification and how transformers work, which is really in the next chapter, but we're going to kind of introduce those concepts today. So silicone-based semiconductor, in its natural state, as silicone is a pretty good insulator. Okay, so it prevents electricity from flowing, but if you add an impurity, then it becomes a pretty good conductor. Okay, back to water. What is water? Is it an insulator or is it a conductor? No. It's a conductor. But is it? Somebody said no just because I'm questioning? Or do you know that for sure? You're right. It's actually really a pretty efficient insulator. So why do they say don't stand in a puddle of water and work with electricity? What's that? Yes is sort of the answer. Impurities. Okay. Where do you see pure water in nature? You do not. Right? The only place you see pure water is if you go to the store and you see distilled water, right? That's pure water. That's water with, it's created and put in that bottle from steam. So the steam comes up, it drops everything back down, it goes into the bottle. You have pure water in distilled water. Whereas distilled water in nature is not, right? So all the water that you encounter has some sort of impurities in it. The impurities might not, be impure the way you might be thinking, but it makes it not pure water. So those impurities change the conduction characteristics from a fairly good insulator to a really pretty good conductor. So what if you took distilled water, you put it in a bucket, and you stood in a bucket? Could you play with electricity and not get shocked? The answer is no. Okay, what do you always have on your skin? Sweat, oils, all kinds of stuff, all kinds of impurities immediately go into that water. You're gonna get zapped. Okay, so a semiconductor is something that under certain circumstances allows electricity to flow well, and under other circumstances it prevents electricity from flowing. So your silicone-based semiconductors, what they will have is, let's just draw it like a big square. I think that just shut all the way off and powered off. Okay, well, I don't think we've been here an hour. So what we might have with a silicone-based semiconductor is two different characteristics of silicone, one with impurities, one without impurities, stuck together. So what we may have is one over here that's got something added to it. I'm not saying that's positive charges, it's just added, right? As opposed to this over here is pure silicone. It's more like poof, pure silicone. All right, so we got, looks like Ted. Added. Okay, so we got some impurities added over here. This is a conductor, and this is then an insulator. Okay, so we use these in the imaging system, and I'll tell you where here in just a few minutes. Okay, so you got any problems with conductors, semiconductors, or insulators at this point? Conductors allow electricity to flow. Insulators disallow electricity to flow. Semiconductors sometimes allow them to flow, sometimes they don't. I'll explain that, if not today, then in depth in the next section. And then we've also got superconductors. And superconductors, two characteristics of superconductors. One is they have to be made of something that has a lot of loosely bound what we refer to as valence electrons, so that they can flow easy. That's number one. And they may make them out of gold. All right. But the second characteristic is because every time we send electricity through a wire, we create heat. That heat adds to resistance, which creates heat, which increases resistance, which creates heat, which increases resistance, right? So in order to reduce that resistance, what we do is we keep it extremely cold. And by extremely cold, I mean extremely cold. MRI uses superconducting magnets, and they're electromagnets, but we have to keep them very cold. And what we use to keep them cold is liquid helium, which is around 400 degrees below zero. Very, very, very cold. Okay, so two characteristics: superconductor, efficient conductor, but we got to keep it cold. All right. almost no resistance, still got resistance, almost no resistance to electric flow. So then we get into electric circuits and how electricity behaves in an electric circuit. And you'll see on page 76, Ohm's law. Okay, so we can manipulate electricity through a circuit by changing some stuff up. So what kind of voltage comes to us from the power plant? You remember? We've got a power plant over here. A nuclear power plant's easier to draw than anything else. We've got a power plant over there, and we send electricity out, and it gets to, on the outside of the hospital, on the telephone pole, we've got that thing in a box we call a transformer, right? So our electricity coming from there may be 500,000 volts. I mean, it's just very, very high voltage. It gets to the transformer and it knocks it down to maybe 220 or 240 volts, and it goes into the hospital. So now we've got a hospital here. You know, I don't know, what's the snake around the staff. So it's in the hospital now. Okay, so we got to get it to the X-ray room, and it's 240 volts. We have to be able to manipulate that to get it up to what kind of voltage? In a word, kilovoltage. Right, we got to get high voltage. So we have to have a way to manipulate it. All right, so the simplest explanation of manipulation is found in Ohm's law, which is V equals IR. Voltage is equal to intensity times resistance. Okay, so if, again, simplify the equation, if we have 1 volt, we have 1 amp, and we have 1 ohm of resistance. A ohm is that 1 ohm of resistance. Is this a true mathematical statement? 1 times 1 equals 1. The answer is yeah. But what if I wanted to increase my voltage and I had the same amperage? I didn't change my amperage. I wanted to increase my voltage. What would I have to do? Change the R. Exactly. So if I wanted 2 volts, I would have to change the resistance by a factor, of 2. Same amount. So if I wanted to maintain the same voltage, though, and why I'd want to do that, I'm not real sure, but I have the same voltage and I increase my resistance to 2, then what's going to happen here? Let's go back to this. 1 equals 1 times 1. If I wanted 2 volts, is that mathematically sound? No. So let's say I want to maintain 1 and I increase this to 2. Is that mathematically correct? No. So what would have to happen? Change amperage, right? So voltage is equal to intensity in amperage times resistance. And if voltage remains the same, these two are, we've got a word for it, inversely proportional, right? Okay, so how do we change resistance? There's a couple of different ways, a number of different ways. One is to, I talked about it a minute ago, we have a wire that's 100 feet long, we're going to have a specific resistance, right? So if it's 100 feet long, I'm not even going to add a resistance value to it. If it's 100 feet long, then the entire length of that, we're generating heat, we're creating more resistance and so on, right? But what if it's only 50 feet long? Less resistance. Less resistance, yeah. So we change the length of the wire. The shorter the wire you have, the less resistance you have. Also, now we're going to take that wire and we're going to turn it so that you're looking straight down onto the wire. If I have a wire that's only this big and my electrons are this big, then how many electrons can I fit on that wire compared to a wire that's this big?
Nowhere near as much.
No, nowhere near as much. Yeah, a whole lot more. Okay. So the other way that you can change the resistance in a wire is to change the diameter of the wire itself. So why is it that we send electricity out of 50,000 or 500,000 volts? Well, it's V equals IR, because it's easier to send high voltage, low amperage down a skinnier wire. Can you imagine how strong the telephone poles would have to be if we had wires this big? You know, that's a lot of wire, right? A thing that big probably weigh about a pound a foot, right? So using Ohm's law, we use very high voltage to send a lot of electricity down a small wire, so that when it gets to this point, what we can do is through transformation, we can, instead of having very high voltage, we can transform it into lower voltage, higher amperage. Okay. So in the X-ray imaging system, we're going to have the same thing. We're going to have transformers. So now we'll go back to this. We get into the imaging system. What's the first thing that electricity gets to? We talked about this just the other day. How much you remember. This first thing. We have to have a way to do what? Increase or decrease resistance. Well, we're going to increase, decrease resistance, yes. But, where was that down here? But what are we going to use? The thing, you remember, talked about the radio, turn it up and down the volume, right? What do we call that? Say it again. Okay, frequency, yeah, radio frequencies. Rheostat, exactly, very good, rheostat. We're going to plug it into a rheostat. It's a type of transformer with one coil of wire. We're up in, I'll tell you what, Wednesday, we're not going to finish up today, obviously, but Wednesday I'll bring an example of transformers down here. We've got a couple of small ones. Okay, so it's a rheostat. And what a rheostat does is it enables you to increase or decrease the power output, right? So the dimmer switch on the wall, your fan control on your heater, you probably needed that this morning, right? It's just a rheostat. So this is our KVP control. So it is a rheostat. It is an auto transformer, and it is KVP control. This is where we set our KVP. We don't have KVP yet. Okay. So the electricity comes out of that, and well, okay. So the first thing actually was I told you about the surge protector, right? So there's line voltage, compensation, and it goes into that. Okay. So you're not going to see this on your machines. It's incorporated into the machine. You're not going to see it at all. It's still registry testable, so you need to understand that there is a line voltage compensation circuit that takes out the fluctuations in the voltage before it gets to the, which is also called the, which is where we set our KVP, right? So it's going to come out of that, and we've got some other things in here that we're going to plug in, later on. And it goes out of that and it goes into the thing that creates our high voltage. So what we're going to have there is two different coils of wire. Now, those two different coils of wire, what we've got is, okay, so comparing these two, would this one be longer or shorter? Shorter, right. There's just a few coils. So the distance between 2 points, the shortest distance between 2 points, straight line, which one is more of a straight line? That one, right? As opposed to this real squiggly thing over here. Got a lot of squiggles in it. So here we're going to have increased resistance. All right. So we've got a few terms on this, what we're going to refer to as the primary side of the step up transformer. We're stepping up the voltage, and this is going to be the secondary side. O is, is secondary, shorthand for secondary side of the step up transformer. So we set our kilovoltage here, and then we run it through this thing and it creates the kilovoltage here. So now we've actually got kilovoltage over here. So we have kVp. It comes out of that and it goes into the X-ray tube, but it makes a stop along the way. So we've got this other circuit right here, and I'm about to describe what that circuit is. But we've got, you know, cathode, anode, we want electrons to jump from this side of the tube to that side of the tube. Right? Okay. Everybody with me, sorta-ish. All right. So here's the next thing in the chapter. We have two different ways that we can deliver electricity. One is through your battery. Through a battery, what you get is a constant flow of electrons. So you plug something in your battery, a flashlight, whatever, you turn it on, GoPro, you turn it on, and what happens over time? It goes out. It goes dead. It goes dead. So you've got this flow of electricity, it just keeps on going until it exhausts the electrons in the battery and that goes dead. But it always goes in the same direction. With alternating current, though, what you get is, again, kind of like what we talked about in electromagnetic radiation. It's a sine wave. So the electricity goes in and it comes out, and it goes in and it comes out, and it goes in and it comes out. You want to hear some sad stories? Look up okay, so Tesla was a big fan of alternating current. Edison was a big fan of direct current. You want to read something really kind of depressing, read how Edison was trying to prove that direct current was a better model than alternating current. It's bad. All right. He didn't prove it either, because we're using alternating current. What you get out of the wall is alternating current. So it goes in and out and in and out and in and out. We have to have alternating current to make these things work. We've also got a secondary circuit that comes off, and that's how we control our milliamperage. Remember that, talking about that? Milliamperage, we have exactly the opposite type of transformer. This is if that's a step up, this is a step down transformer, right? Now, the reason I'm pointing all this out is because if we have alternating current, that means the current's trying to go in that direction, and then it's trying to reverse direction and go opposite direction. Okay? So we have to have alternating current, and we'll talk about why later on, but we have to have alternating current to make this work. We have to have alternating current to make this work. But what happens if we have current that flows from the anode, which is a big solid chunk of metal, you know? Pass that around, didn't I? Showed you what that looked like. Big solid chunk of metal, that those electrons going from here to there can melt. What happens if the electrons go from here to here? Your tube is done, right? Single hit and your tube is trash. So X-ray tubes, cheapest X-ray tube is probably $10,000. You get into CAT scan, $60,000, $70,000 easy. Okay. So do you want this to happen? The answer is no. So we have to have alternating current. Alternating current means electricity is going in one direction, comes back in the opposite direction. It oscillates 60 times per second at 60 hertz. Goes back and forth. We have to have alternating current to make that work. We have to have alternating current to make it work out on the telephone pole. It has to be here, has to be here, got to get rid of it. Okay? So that's what this circuit is all about. Okay, now it brings it all the way back to semiconductors. What is a semiconductor?
It works in control.
It makes electricity, it'll allow electricity to flow one direction. It will keep it from flowing in the opposite direction. So let's simplify this a little. We're going to take this circuit out, and we're just going to put a semiconductor here that will allow electricity to flow in that direction, but whenever it tries to come back, it won't come back. Okay? Let's put another one up here. It'll allow electricity to go in that direction, but whenever it tries to go in that direction, it'll kill it. Now, did we prevent this from happening?
Yeah.
Answer is yeah. Okay. semiconductors keep our electricity flowing, and it changes our alternating current. We have to have alternating current, have to have direct current. So our semiconductors, and again, I'll explain exactly how those work later on. Our semiconductors are going to prevent the reverse flow to keep our electricity from damaging our X-ray tube. So we change our electricity from alternating current in the semiconductor, the rectification circuit. The rectification circuit changes our alternating current to direct current, so we don't destroy our tube with a single exposure. So some of this is much more than what you need for this particular test, right? But why learn the material without understanding a little bit of the application? And just memorization at that point, and then you got to dig it back up. You've got to be tested over this eventually, but I think let's see, induction, informal law. What may be this? No, it's actually chapter 6. So you don't have to understand how the semiconductors work, but what you do need to know is alternating current. And you have to have it here. You have to have it here. You have to have it here. You hate it here, right? So you gotta get rid of it. What's our time? 51 minutes. Okay. All right. Any questions on all that? So what do you need to know?
Alternating current until it hits two.
Until it hits 2. You need to know semiconductors do what? Allow one way, not the other. Conductors do what? Allows them to go, right? Insulators do what? Prevents superconductors. 2 elements of superconductor.
Loosely bound valence electrons. It's really cold.
Very good conductor, and it's got to be kept very cold, right? And what else do we talk about today? Electrodynamics, potential circuit. Oh, yeah. Ohm's law. Ohm's law, if voltage remains the same, then intensity and resistance are inversely proportional. Voltage is going to be directly proportional to a change in either one of those things, providing the other one remains the same, which means you double your intensity while resistance remains the same. And to get that same number of electrons through that conductor, what are you going to have? More voltage. Yeah, voltage is going to have to increase, right? So let's say your resistance increases, your wire gets skinnier. What are you going to have for voltage to remain the same?
Higher intensity.
Yeah, higher resistance. Your resistance increase, so amperage is going to decrease, right? Right. Okay. Are you saturated? Done? Because we got time. We can get into some more stuff, but are you filled up? You filled up? All right. Let's call it good then. We'll pick up there. This test is probably not going to be before, well, it won't be before next Friday. And it, in all likelihood, will be, the Wednesday after. So we still got a lot of chapters left. Okay. All right.